Hi everyone, so this is the last section of chapter 1 that we are going to be looking at. And this is section 13, and it looks at linear and exponential change. And it's pretty closely related to the last section that we looked at, section 12. So a function is a rule that assigns a value of the independent variable known as the input to exactly one value of the dependent variable known as the output. The input, again, is also known as the independent variable, and it helps that those ones start with the same letter. And the output is also known as the dependent variable. And if we think of it in a table, almost always we have our input on the left and our output on the right side. When we have our graphs, the independent variable or the input will be on the bottom, and the dependent variable or the output will be along the side. We can say that the dependent variable is a function of the independent variable. Functions can be displayed as graphs, tables, and equations. I kind of also like to think that the dependent variable is a response to the independent variable. I would go ahead and take a little bit of time and read through this. I won't read it to you, but it's something that you can look at on your own. So you can go ahead and pause the video and read through this in your note packet. Okay, we will often be presented with a situation or problem that we want to understand better. To do so, we determine the variables involved and their relationship to each other using a process known as modeling. In this book, we will often model a situation by looking at changes we see in a table or graph and find patterns in those changes. Based on those patterns, we will write an equation to describe the situation and use the table, graph, or equation to analyze the situation further. Although many kinds of functions can be used to model data, the example in the explore problem that we just looked at provides two common types, are linear functions and exponential functions. Let's look more closely at these types of functions. So suppose the owner of a new company has the goal of gaining 500 new customers each fiscal quarter. So each fiscal quarter is also, you can think of as every 3 months. Write a function to model the relationship between the number of fiscal quarters and the total number of customers. Use the table, graph, or equation to determine how many customers the company should expect to have after 5 years and how long it will take to reach 100,000 customers. We can begin the problem by constructing a table, a graph, or equation. In this example, we will look at all three to see each representation of the function. We start with no time having passed for the company and 0 customers. So at this spot right here or at this spot, it is at 0 quarters, so 0 time passing, and 0 total customers, and same for the table. From there, in each additional quarter, so we see the quarters increasing by 1, in the graph and in the table, we have the total number of customers increasing by 500. So we can see that the number of customers is increasing by 500 for each quarter. We can label the expression of the nth term in the sequence as total customers. The equation formed another way to represent the function where n is equal to the number of quarters. So if we look at this, it even shows us right here the total number of customers after n quarters is equal to 500n. So all of these values can be found by taking 5 times n, and n is just what our quarter number is. So we can write an even fancier equation, and we can write the total customers is equal to 500n. So we're going to use the info to find the following. The first one wants us to find the total number of customers after 20 quarters. So in this case, they're telling us that n is equal to 20. So I can write my equation to start and say the total customers is equal to 500n, and we know that n is equal to 20. So my total customers will be equal to 500 times 20. And so we will get 10,000 customers. For part B, this one's a little bit different. In this one, it says how many quarters will it take to reach 100,000 customers. So I'm going to start with our general equation. Total customers equals 500n. Well, this time they give us the total number of customers. So it's going to be 100,000 plugged in here. And this time I'm going to be solving for n. So I'm just going to take and divide both sides by 500. And we end up with 200 for n. So this is going to be after 200 quarters. A function whose outputs increase or decrease by a constant amount when the inputs increase by 1, there is a linear function. Therefore, the function values form an arithmetic sequence. So we learned in the last section that when we have addition or subtraction, that is going to be what we consider to be arithmetic. What we're going to notice today is the link between arithmetic and linear. So when we see growth, if the function values are increasing, then that is what we consider to be linear growth. If the values are decreasing, then the function represents linear decay. You can see here that this one, remember that we read graphs from left to right. So this one, when we read it, it goes from down to up. So this would represent growth. This one represents decay because when we read it from left to right, it goes down. So for example, if Facebook gains 1 million new users each month, then the number of new users is a linear function of the number of months. To use a table to determine if a function is linear, you're going to find the amount of change in the function values when the inputs increase by 1. The amount of change should be a constant value if the function is linear. The points can also be plotted to see if they fall in a line. Conversely, if we know the data has a linear change, we can connect the dots with a line as we did in the previous example. So this one is going to be really important. This is your equation that you will use for any linear function. They will all look like this. You will have your dependent value, and that will be equal to your starting value plus the amount of change times the independent variable. When the starting value is the 0th term of the corresponding arithmetic sequence. So we're always going to have our start value be at 0. So something to note here. For this one, we're going to create a linear function using that equation format that we just saw right there. So right here, this is something really important. our starting value is what y equals when x equals 0. So for this one, we see that x is equal to 0. So negative 18 will be our starting value. These on the left are your inputs or your independent variables. On the right here, these are your outputs or your dependent variables. This one, you can see that these are increasing by 1. So we can use that to find what our change is. So we're going to look in the output area to see what the change is. We can see it's going from negative 18 to negative 12 to negative 6 and so on. So these are increasing by 6. So if we were to even look at this as like a list like this or just a sequence like this, we would see that it is an arithmetic sequence, which means then that it's a linear function. All right, so we're going to go ahead and we're going to just we're going to write down our setup for what a linear function looks like. So it's our dependent variable equals our start plus the change times the independent variable. Remember that your dependent variable was y. Our starting value was negative 18. Our change was negative 6. And our independent variable was x. So if we write this in a nice, cleaner way, we can say that y is equal to negative 18 plus negative 6x. But that's a little bit awkward to write it like that. So a better way of writing it would be to write it as y equals negative 18 minus 6x to represent that it's decreasing. Example 3, you have an interest-free loan of $800 and are paying it off at a rate of $50 per month. Model the situation with a table, graph, and equation. Is the function a linear function? How many months will it take to repay the loan? So in this example, we have a table that has not completed yet, but we do have a graph that was completed for us. So with this one, our starting value is at $800 because that is what we are starting with, or that we're beginning with that amount. The change, we're paying it off at a rate of $50 per month. So that means that we are having a change of minus 50 because we're paying off an amount of $50 per month. So it's going to decrease by 50. All of these are going to be our independent variables. Our independent variable, which is going to be the months, and we can also consider this to be our input. And then we have our dependent variable, or our output, which will be considered A. And you can see that the independent variable is here and the dependent variable is here on our graph. When we look at this, we want to start at month 0 and we want to go increase by 1. So we would go 1, 2, 3, 4, and 5. Now we're starting with $800. And our change we mentioned is minus 50. So we're going to go minus 50 every month. So this will be 750, and then 700, and then 650, 600, 550. So when we look at this, our function is going to be remember that the setup is going to be our dependent equals our start value plus our change times our independent variable. So our independent variable for this one is m, that is our independent, and our change is minus 50, so we can even just write it as minus 50. Our starting value was 800, and our dependent variable is A. And it would look a little bit nicer if I write it like A equals 800 minus 50, so we don't really need the parentheses there. And so this is yes, this is linear. We have a linear change happening here. The other question it says is how long will it take to repay the loan? If we repay the loan, that is when the balance will be 0. So instead of having A, we're going to have A is equal to 0. So we're just going to replace A with 0. So 0 is equal to 800 minus 50m. So to solve, I'm going to subtract 800 from both sides. So we have negative 800 equals negative 50m. Divide both sides by negative 50. And we get m is equal to 16, and this would be 16 months to pay back the loan to get it to a balance of 0. So linear functions are useful for situations with changes that are constant amounts, and some situations involve change that is not a consistent amount, but rather a consistent percent. And we're going to look at this kind of change as a type of function and a type of function to represent it. So in the next example, example 4, we have a virus is contracted by 100 people, each of whom infects 2 more people the first day, after which they are no longer contagious. We're going to write a function to model the number of new people infected each day by the virus. Assume that the infection will continue to spread from each sick person to 2 additional people. You will use the graph, a table, or equation to determine how many new people will be infected on the 14th day. And then you'll determine the day on which the number of new people infected this day is at least 100,000. So if we look at this at day 0, we've got 1 person. At day 2, we have 2 people. So we can see that these are increasing by 2. It's 2 people each. By day 2, we have 2 more people. 2 more people, so that would be 4 total people, or multiply the previous one by 2, and so on. Using this idea, we can look at what we would have with our table and with our graph. So those are already completed for us. For this one, I will just kind of give you guys how to do this one, and we're going to look at what the setup will be like for these types of equations. But you're going to take your starting value, which would be the number of people infected at day 0, times 2 to the power of n. So these are going to be exponential functions because they change by a percent. I'm only going to have us look at what would happen if we look at how many people are infected by the 14th day. So we're going to substitute the 14th day into the equation for n. So we're going to start with our original equation, and we're going to replace n with 14. So you will use your exponent button and have 2 to the 14th, which will give you 16,384. And you'll multiply that by 100 to get 1,638,400 people. So we can say there will be 1,638,400 people that would be infected by the 14th day if this continues. So an exponential function is a function whose outputs experience a constant multiplier as the inputs increase by 1. Therefore, the function values form a geometric sequence. So similar to what we were looking at with arithmetic and linear, there is a relationship between geometric and exponential. If we see exponential growth, like this one right here, we can see that from left to right, these values are increasing. And if the values are decreasing, that will represent exponential decay. Okay, on the next page, we will look at what our setup will look like. So for example, if the number of new Facebook users triples every day, the number of new Facebook users is an exponential function of the number of days. The number of new users on day 2 is 3 times as large as the number of new users on day 1. The number of new users on day 3 is 3 times as large as the number of users on day 2. So for our multiplier, to use a table to determine if there is an exponential relationship, you will find the multiplier between the function values as the inputs change by 1. The multiplier should be a positive value. And if there is an exponential relationship in the data, a curve, not a line, but a curve, can be drawn on the graph connecting the points. So our setup for our exponential functions are a little bit different. We still have our dependent variable on the left, and we still have it equal to the start value times, and in this time it's going to be times our multiplier. And then we're going to have an exponent of our independent variable. So the independent variable will be the exponent. So looking at this one, it says a company wants to project growth using both linear and exponential change to see the long-term effects. The company begins with 150 clients, so this would be our starting value. The CEO wants to project growth, assuming a 10% growth in the client list each month. So with our multiplier, this is going to be an increase. So it's going to be 1 plus 10% as a decimal. So this is going to be 1 plus 0.10. So we get 1.10. That is our multiplier. Now, when we think of the other thing that we need to figure out which variable is going to be our independent and which is going to be our dependent. Remember that the dependent variable is the response to the independent variable. So when we think of the number of clients, that would be a response to how long it has been since the company is open. So we're going to have our months be our independent and the number of clients be our dependent. So it says that C will represent the number of clients and M will represent the number of months. So our setup is dependent equals the start times our multiplier and then times our independent variable, or to our independent variable as an exponent. So we have C for our dependent variable equals the start value is 150. Our multiplier is 1.10, and our independent variable is M. So this would be our function. Looking at our last example, example 6, city planners for a city with a current population of 100,000 residents are modeling the population in various ways to help them make decisions related to resources. For each scenario, you will write a function. So for this one, our starting value for each of these is going to be 100,000. So that will always be our start. Now, on some of these, remember that if it's linear, that has an increase or a decrease that is using addition or subtraction. If it's exponential, that is going to be using a multiplier, or we can also think of it as multiplying or dividing. So those are the differences when we think of linear versus exponential. So the first thing that I would want us to do when we start these is to look at which of these scenarios is going to be linear and which is going to be exponential. For A, it says a population increases by 5,000 residents per day. So that's an increase of 5,000, so that would be using addition. So this one will be linear. When we look at B, it says increases by 8,500 residents per day. So that one is also addition, so we would also see linear. For C, it says it increases by 2.5% each year, so this would be as a multiplier, so this would be exponential. And this one increases by a percent as well, so that's with a multiplier, so that would also be exponential as well. When we think of our variables for each one of these, we have the number of years and we have the actual population or the number of residents. So we have the number of years is going to directly impact the overall population. So let's go ahead and make N represent the number of years, and let's make a P represent the overall population. So you can also think of this for your input and your output. P is going to be N is going to be your input or your independent variable. P is going to be your output or your dependent variable. With linear equations, so for these two, you are going to be using this setup. Our dependent variable is equal to our start value plus our change times our independent variable. So for each of these, all of them are going to have P as the dependent. So this will be P equals, and this one will be P equals. All of them will have a start of 100,000. That does not change. So the 100,000 is always going to be there. Then when we think about our change, this one is increasing by 5,000, and that will get multiplied by the independent variable, which is always going to be N, the number of years. This one is increasing by 8,500, and that will also get multiplied by N. For these ones, you're going to be using the exponential function. Your exponential function is the dependent equals the start value times your multiplier, and then the exponent is your independent variable. So all of these will start with P equals, and it'll also start with 100,000 as your starting value. Your multiplier for this one is going to be 1 plus 2.5 as a percent, which would be 0.025. So we would have 1.025. And our exponent is going to be N, the number of years. This one is very similar, except our multiplier will be 1.03, but N will still be our exponent. Okay, and just as a heads up, you guys will not have to cover section 1.14. 1.14 has been taken off of our list of required sections, so you will not have homework on it, you will not have a test on it, it will not be part of our curriculum this semester. Okay, if you have any questions, please feel free to reach out. Have a great day, everyone.